set 2 specimen paper walkthrough. Question 1 deals with water and the states of matter. Reading this, the particles are arranged in a regular pattern, suggests that it's a solid, so the answer to this one is going to be ice. Particles are close together but not in a pattern, that's a liquid, so water is our liquid in this one. Particles move quickly in all directions is a gas, and steam is the example of a gas in this instance. Which will have the most internal energy, so that's essentially temperature. So your steam, which is a gas, is going to have the most energy. So this will have the least, then water, then steam. Lowest density, again, will be the gas, so steam once more. Here we've got a density calculation. So density is mass divided by volume. We just have to substitute mass, which is 11,200 kilograms, and the volume 12 meters cubed. So density is mass over volume equals 11,200 over 12. Calculations, it's given as the equation. Density is mass divided by volume, so that is 11,200 over 12, which gives us 933.3 reoccurring, which will just round to 3 significant figures, as these two values are, so 933. Explaining why the iceberg will melt. So the surroundings are at a higher temperature than the iceberg, so energy will flow from the surroundings into the iceberg, increasing its internal energy. Okay. Question 2 looks at 3 different components. We have A, this is the symbol for a variable resistor, so a rectangle with an arrow. We have a light dependent resistor, so it's just again the rectangle for the resistor in a circle with 2 rays of light coming in. And finally a thermistor, which changes resistance based on temperature, whereas the LDR changes resistance with light. The component that's a variable resistor, obviously that's going to be A. Thermistor will be C. In which component will the resistance decrease when the temperature increases? That's going to be the thermistor, so again C. In which component will the resistance decrease when light intensity increases? That's got to be the light dependent resistor, which was B. Moving on to 2.5, we've got 4 different arrangements of resistors. We've got 2 series networks and 2 parallel networks. The difference between the 2, series only has a single loop or pathway through which the current can flow. Parallel, you have branches, so it can separate off into branches. Which arrangement has a resistance of 10 ohms? So let's have a look at these. With series, you just add them together, so 5 plus 5 is 10. So we have R. Which arrangement has the highest resistance? If you have 10 plus 10, that will give you 20. With these, having two resistors in parallel actually reduces the overall resistance, so it can't be either of these two. So we're looking at speed. A student connects a resistor to a cell for 60 seconds. The current through the resistor is 0.97 amps, and we're using the equation charge flow equals current times time. Calculate the charge flow. So Q, which is the symbol for charge, is I times T. So I, the symbol for current, T, the symbol for time. We have 0.97 times 60. I'm going to pop that into the calculator. So 0.97 times 60 gives us 58.2 coulombs. And again, with calculation questions, don't forget to write the answer you want marking in the bottom corner so the examiner knows what they're looking for. Moving on to question 3. Shows a 3-pin plug connected to the cable of a metal toaster. Name wire X. So if you were to see this in colour, it would be yellow and green. The yellow and green wire is the earth wire. You'll have the live wire, which would be brown, the neutral wire, which would be blue. What does wire X do? It can prevent an electric shock from the toaster. So it's a safety device within the plug. 3.3, the toaster is plugged into the mains electricity. What is the potential difference between the live and neutral wires? So in mains electricity, you're going to have 230 volts. Two difference between an alternating supply and the direct supply. Your DC, your direct supply, is always constant, unchanging, and another difference is the alternating supply can be negative, whereas your DC would never be negative. Here we have a graph. You'll need to be very good at interpreting graphs, they will come up a lot. So energy is transferred to homes by the national grid. Figure 6 shows the percentage energy losses over the national grid for different years. So this looks to be 1.92. So I'm just having a look at the graph, seeing what it tells me before I even look at the questions. So 1.72, 1.70, 1.74 and 1.77. So since 2011 we've had an overall decrease, but with a small rise since 2013. Calculate the mean percentage energy loss per year in figure 6. So to work out a mean, just add all the values together and divide by the number of values we have. So we have 1.92, 1.72, we have 1.70, 174, and I think the last one was 1.77. Good. And there are 5 values, so dividing everything by 5. It's always quite good practice to put brackets here, just in case you make an error typing it into the calculator and it just divides the last number by 5 rather than the whole lot. So let's tap that into our calculator. 1.70 plus 1.4 plus 1.77 divided by 3. I made an error there, so 1.92 plus 1.72 plus 1.70 plus 1.74 plus 1.77 divided by 5 gives us average of 1.77. So a quick check to make sure that your mean value lies in between your lowest and your highest. If it doesn't, then you've done something wrong. So again, right down the bottom there. Question 4 starts off with a specific heat capacity question. So we're placing 0.5 kilograms of potatoes, so this is our mass, into a pan of water. During cooking, the temperature of the potato increases from 20 to 100, so we need to work out a temperature change here. So what have we increased by? So simply 100 minus 20 equals 80 degrees C, so that's going to be our change in temperature. We've got a specific heat capacity of a potato, 3,400, so not as high as water, but still quite high. And we're using the equation, change in thermal energy is mass times specific heat capacity times temperature change. So again, E equals M times C times delta T. Mass was 0.5 times 3,400 times by our 80 degrees that we worked out a second ago. And again, we'll type that into the calculator. 0.5 times 3,400 times by 80. And it will be joules. So 136,000. So I'm doing this off the screen because I have my phone, not a calculator, which is a little bit annoying, but we'll do what we can. What is the energy supplied by the why is the energy supplied by the cooker greater than the calculated value in 4.1? So energy will be transferred to the surroundings. So you're not just heating up the potatoes, you're going to be heating up the water, you're going to be heating up the stove and the atmosphere as well. So this is just a good coverall response. Suggest one way the student could reduce the time to heat up the potato. So if we look here, you're losing lots of heat energy to the surroundings purely because you don't have a lid. So if you were to place a lid on top of that, that would stop convection and it would happen a lot faster. So use a lid. So we have an efficiency calculation now. So our total energy in is 500, useful power out is 300. So for our efficiency, useful power out over the total power, so 300 over 500, and that should be equal to 0.6. So they haven't asked for it as a percentage, so we'll just leave it as a decimal. If we were to times it by 100, we get 60%, but this is what the examiner is going to be looking for. The jug is made of plastic with a low thermal conductivity. Explain why this is an advantage. So if we look at the jug, here are the blades. So if you're blending something hot, you don't want to burn yourself on there. So this is an advantage. So food stays warm. And also you're not going to burn yourself. Picture of a girl riding a self-balancing scooter. It's got an electrical motor powered by a battery. During the ride it transfers 15,000 coulombs of charge. The potential difference is 36 volts. So here energy transferred equals charge times potential difference, and it's asking for your answers in kilojoules. So this is going to make it a little bit tricky because we'll need to convert our joules into kilojoules at the end, and to do that we simply do joules divided by 1000, but we'll come on to that in a second. So energy equals charge times potential difference. So Q the symbol for charge, V the symbol for potential difference, E for energy obviously. 15,000 times by 36. Okay, pop that into the phone. gives us 540,000 joules. Now to convert that into kilojoules, we need to divide it by 1,000, and that will give us 540 kilojoules. Again, write it in the space down here so the examiner knows what he's marking. Explain why scooter B has higher maximum speed for 2 marks. So if we look at these, they've both got the same efficiency, so the same proportion of useful energy is going to be produced by both of them. This one's got a greater mass and this one has a significantly higher power. So scooter B has higher power and the same efficiency, so you're going to get more kinetic energy out. Both scooters can be ridden for 20 minutes before the battery needs recharging. Compare the amount of chemical energy stored in the batteries of each scooter. So they both last the same time. Scooter A, again that's the 500 watt one, scooter B is the 700, so if they both last the same amount of time, then scooter B must have more energy in its chemical store. So scooter B must have more energy in its battery. Write the equation that links down energy transfers, power and time. So energy is equal to power times time, and this is one of those ones that you just have to remember from the formula sheet. So calculate the energy transferred by the motor in scooter B in 20 minutes. So scooter B, so the power was 700 watts. The time, they're trying to capture this out here, they're giving us 20 minutes. Now what you're most likely to do is just write down 700 times 20, but we need to actually convert this to seconds first. There are 60 seconds in a minute, so we do 20 times 60 gives us 1,200 seconds. So E equals P times T. P 700 times by 1,200, and we'll get the old calculator out again. 840,000 joules. So they're not asking for us to give it in kilojoules this time, so we'll just leave it like that as it is. So student investigates the length of resistance, so how length affects the resistance of a wire. Figure 10 shows the circuit the student used. So we have a fixed resistor to make sure the current doesn't get too high in the circuit. We have the wire which we're testing the resistance of and changing the length. We have a meter Y which is connected in parallel to the wire. We have meter X which is connected in series, and then we have the meter rule. If it's connected in series, it's got to be an ammeter. Always connect your ammeter in series, and your meter Y is a voltmeter which is connected in parallel. Think about measuring the current through something and the voltage across. That's a way to remember it. So we have a table of results here, and it's asking us for which length of wire are the readings of the resistance most precise. Now that means the closest to the true value. So what we're looking for is the set of data which has the smallest spread away from the mean. So if we look at this row here, 2.02, 2.02, 2.03, and the mean is 2.02. So the furthest value we have away from the mean is only 0.01, which is closer than all the others. So this is what we're looking for. So 0.300, and it has the smallest spread of results around the mean. Why did the student do 3 tests and calculate a mean? So it reduces error and improves accuracy and allows us to spot anomalies. So any one of those 3. Write down an equation that links current, potential difference and resistance. So V for potential difference equals current I times resistance V equals I times R. The potential difference across the wire is 2.1 volts. The current in the wire is 0.3, so calculate the resistance. So we'll need to rearrange our equation from earlier, and to do that, let's put it into a formula triangle. So it's I times R, so we'll put those on the bottom like that, and that leaves V to go up above. We're trying to find out R, so we cover up R, leaving us with V divided by I. So R equals V divided by I. 2.1 over 0.3. We'll pop that into the calculator, and I think we're going to get something like 7, but bear with me a moment. Yep, 7 volts. 7 ohms, beg your pardon. What is the label for each axis of the graph? So this x-axis starts at 0. This x-axis starts at 0, goes up to 0.700. The y-axis starts at 0, goes up to 4.5. So let's have a look at our table on the previous page. So the length in meters starts at 0.1 and goes up to 600. So that suggests to me that that's what's going to be on the x-axis, and the mean resistance in ohms, that's what's going to be on the y-axis, because that goes up to 4. So x-axis, length in meters, and y-axis will be mean resistance in ohms. So that's the symbol for ohms there. It's important to put your units in as well, so you would not get the mark if you didn't use the units. What conclusion can be made from the graph in figure 11? If we look at it, we have a straight line it's got a positive gradient and it goes through the origin, so through 0, 0, so that's got to be directly proportional. So if you meet these three criteria, your relationship is directly proportional. So length is directly proportional to resistance. So moving on to the last question. So we have radioactive sources. Radium-226 gives off alpha, beta and gamma, and there's a few warnings. So these are the warning symbols for radiation, and you need to be careful. Use forceps. Always direct the open end away from the person. So we have a half-life graph here. It looks to be starting our line at 184,000. 184,000, well, half of that is 92,000, so that looks to be around here. And then you follow across with a ruler, obviously, until you hit this line, drop down, and we're looking at about 1600 years. So 184, that's where we start, divided by 2 gives us 92,000. Reading off from the graph, it gave me a half-life of 1,600 years. Radium-226 was discovered by Marie Curie in 1898. The notebooks she used were contaminated with radium-226 and they're still hazardous. Explain why this is. Well, 1898 was, what was that, 120 years ago. So contaminated 120 years ago. Half-life of radium is approximately 1600 years. 120 is a lot less than 1600 years, so the books are still going to be radioactive. So the radiation just hasn't decreased. Last question. So explain how the properties of alpha, beta and gamma radiation affect the level of hazard at different distances. So alpha is most ionizing, so it causes the most damage to cells, but has a range in air of only a few centimetres. So at short distances, so alpha will be the most hazardous. So your beta particles consist of an electron, a fast moving electron emitted from the nucleus. So beta is moderately ionizing, and has a range of about 1.5 to 2 meters in air. So I think 1.7 is the exact value. So 1.5 to 2 meters in air. So it is most hazardous at medium ranges. Gamma, so it's an electromagnetic wave, so theoretically its range is limitless, but it does dissipate it does dissipate in accordance with the inverse square law, so it will decrease with distance, but it's the least ionizing. So gamma is least ionizing but can act over large distances, so most hazardous at long range. Okay, thank you very much.